Look at this intense sunlight baking the East African savanna. For our earliest modern ancestors, surviving under this blistering equatorial star meant adapting to massive, relentless amounts of ultraviolet radiation. Now look at this pale, low-angled northern sky. Thousands of years later, descendants of those same humans settled in high-latitude regions where direct sunlight is incredibly scarce. If we trace the migration from the equator to the Arctic, we see a dramatic shift in human pigmentation. While common language frames this as a linear progression from black to white, the biological reality is far more complex than a simple forward march. To understand what actually happened, we have to start here, with our early human ancestors living near the equator. The variation in human skin tones you see today acts as a biological map. It charts the way human populations adapted to survive as they spread across rapidly shifting global climates. When early hominids moved out of shaded forests and into open savannas, they needed to hunt and run without overheating. They lost their thick body hair to allow for sweating, but this left their bare skin exposed to intense equatorial radiation. The true danger of this radiation was the destruction of folate in the bloodstream. Folate is an essential nutrient required for healthy fetal development and successful reproduction. Without it, a population's ability to sustain itself would collapse within a few generations. Dark pigment melanin acts as a biological shield. These melanin clusters form a dense barrier, absorbing and deflecting incoming UV rays to keep delicate folate molecules safe. With this barrier in place, high-intensity sunlight is neutralized, allowing our ancestors to thrive. Deeply pigmented skin was humanity's first major survival adaptation. This calibrated biological shield ensured the continuation of our species in its ancestral homeland. As human populations grew, they migrated out of Africa, pushing into challenging new landscapes with vastly different climates, and critically, much weaker sunlight. This created a biological paradox. While the sun destroys folate, the human body also requires UV radiation to synthesize vitamin D. This nutrient is essential for building strong bones and maintaining a functioning immune system. This scale illustrates the crisis. The melanin shield protected folate, but blocked scarce UV light needed for vitamin D, causing levels to crash. In colder climates, weak bones meant death. Over generations, the melanin barrier thinned, allowing UV rays through to restart vitamin D production. Dropping the melanin shield allowed humans to survive in low-light environments. Without this adaptation, northern migrants would face lethal vitamin D deficiencies that threatened their existence. These migrations did not follow a single path. Humans splintered off, spreading across vast, distinct northern environments, from European ice ages to Central Asian grasslands. If you look at a light-skinned person of European descent and a light-skinned person of East Asian descent, you face an interesting question. Did they inherit their lighter pigmentation from the exact same mutated ancestor? By sequencing ancient DNA from archaeological sites, geneticists found the answer. Europe and Asia solved the low light problem using completely separate genetic pathways. Watch these two DNA strands. This is convergent evolution. European mutations in genes like SLC24A5 triggered pigment loss, while East Asian populations used entirely different genes to achieve the same result. This genetic complexity allows human skin to fine-tune itself to local UV levels. Lighter pigmentation is an adaptive solution that nature independently invented multiple times in different parts of the world. But biology doesn't operate in a vacuum. Inuit populations in the extreme north live in incredibly low UV environments, yet they retained relatively darker pigmentation. Based on the environmental pressure we just mapped out, the extreme lack of sunlight should have led to a near-total loss of melanin to allow for vitamin D production. The solution to this anomaly is found in their traditional diet. By consuming large amounts of marine life, like fish and blubber, they ingested massive quantities of vitamin D directly. Because their diet provided the nutrient, their bodies never faced the pressure to lose their melanin. Evolution follows the path of survival. When a specialized diet resolves a biological crisis, the genetic pressure to change skin color completely disappears. Look at this map. This is the grand result of humanity's evolutionary balancing act. global skin tones map onto a gradient of UV intensity, moving seamlessly from the dark pigmentation of the equator to the lighter tones of the poles. This fluid spectrum, driven by the body's need to balance folate and vitamin D, shows how human appearance shifts gradually across geography. When we look at this continuous gradient, the idea of drawing sharp biological boundaries between populations becomes impossible to sustain. Skin color is a highly visible adaptation, but it represents a tiny fraction of our genetic makeup. Beneath the surface, all human populations are extraordinarily similar, sharing the same fundamental DNA. The next time you look at human skin, remember where the journey began. Our skin colors reflect millions of years of adaptation to local environments. They record our ancestors' travels, their survival, and the elegant ways evolution shaped us all to thrive under different suns. If you enjoy uncovering the hidden stories of human history, subscribe to Human History Explained.